Welcome to NOAA Live Alaska. My name is Lisa Hiruki-Raring and I'm going to be moderating today's webinar. This series is a collaborative effort by NOAA Fisheries Alaska Fisheries Science Center, where I work, NOAA's Alaska Regional Collaboration Network, and NOAA's National Weather Service. This is the fourth webinar in a series that we designed to help you get to know NOAA's work in Alaska and how we connect and work with your communities. NOAA, the National Oceanic and Atmospheric Administration, studies the ocean and the atmosphere and where the two meet, from the weather to the ocean to the animals that live around us. All of our speakers work for some part of NOAA or work in partnership with NOAA. Today we're introducing you to Jessica Murphy and Lieutenant Junior Grade Michelle Levano from NOAA's Office of Coast Survey in Seattle, Washington. While we'll be talking about NOAA's role in research and stewardship, we also want to recognize that we're all coming to you from the traditional lands of Native communities who have substantial traditional and local knowledge and much to share with us. NOAA's Office of Coast Survey does work in all U.S. waters, and Jessica and Michelle's work is conducted all along Alaska's coastlines from the Arctic to the south to Southeast Alaska, which from north to south are the traditional home waters of the Inupiat, Yupik, Inunga, Alutiiq, Eyak, Tlingit, Haida, and Tsimshian people. We'd also like to acknowledge that we are hosting this webinar from the traditional lands of the first people of Seattle, the Duwamish people, past and present. A few guidelines before I hand you over to our speakers. You're all muted because we have a lot of people on the line and we want to make sure that everyone can hear our speakers. However, there's a box where you can write questions. We encourage you to ask them as we go, and my colleague Chris Beyer and I will be keeping track of questions for Jessica and Michelle. They'll stop every now and again and answer a few questions. We may not get to all of our questions, but we'll try to answer as many as we can. All right, I'll hand it over to Jessica and Michelle to introduce themselves. Oh,
great.
Michelle,
Thank you, Lisa.
are you muted? Oh, there you are. Okay.
Sometimes it just takes a second for it all to begin. And so again, thank you, Lisa. We are here today to talk about how we use sound to map Alaska seafloor. And with me, we have Office of Coast Survey's own member of the Pacific Hydrographic Branch, Jessica Murphy. And we're going to start off our presentation with just a brief introduction of each of ourselves. Again, my name is Michelle Levano. I am the team lead for the navigation and response team here in the Pacific Northwest. And I am a native of Long Island, New York, and kind of grew up a little bit around the water. My dad always used to joke that I had this very stern and serious face on whenever they put me in front of the wheel of the boat to drive the boat. So he said that this was always a career destined for me because I always had the face of the disappointed captain. But anyway, I have been with NOAA now for 5 years, and I absolutely have enjoyed my time completely here. I've sailed from the Aleutians down to San Diego, California, and have been able to respond to a number of hurricanes so far. My career with NOAA has been very much based in hydrographic mapping and making sure that the nation has updated maps or nautical charts of the ocean bottom so that ships can navigate safely.
Okay, thanks, Michelle. So everybody, my name is Jessica Murphy. I am a physical scientist at NOAA's Office of Coast Survey. So what that means is that I'm interested in the physical characteristics of the ocean or the physical characteristics of the seafloor. So what does the seafloor look like? How deep is it? What is it made of? Is it hard? Is it soft? So those are the physical characteristics of the seafloor. And I've been working with NOAA for about 7 years. I grew up in north central Texas, so not really near the ocean. I was a little scared of the ocean when I was younger. The first time I got in, I got caught in a current and got seaweed wrapped around my legs, so I was terrified to go back into the ocean after that. But I did. I got over that fear, and I've done a lot of snorkeling and scuba diving in my life. I got a degree in marine biology, and then I got a master's in environmental science. And I've done several jobs. I've worked in and around estuaries in Washington and Oregon doing Dungeness crab abundance research. And I interned doing forest mapping in Oregon. So I mapped the forests, and now working with Michelle, I work to map the seafloor. And one of my favorite things about my job now is that I get to travel to Alaska and see Alaska. And when I do get to travel and go out to sea, I love looking at or watching the sunsets and the sunrises. I think everybody loves that when they're out at sea. It's one of the most beautiful things you can see when you're out there. So today, that's a little bit about myself. Today, Michelle and I are going to talk about why it's important to survey the seafloor, how we do that using sound. We're going to talk a little bit about the tools that we use, the data that we collect, and what that can tell you about the seafloor. So I'm going to hand it over to Michelle, and she's going to start the presentation.
Great, thank you, Jess. That was a perfect introduction into the overview of what we'll be talking about today. So as Jess mentioned, we're going to talk about why we care about what's on the ocean bottom or the seafloor. And we mentioned a couple of things so far, as in ocean mapping and making sure boats can get to and from safely. But there's a bunch of other things that we do use this data and information for as well. One of them being fish habitats. So we can use the information and data that we collect on the ocean bottom to model how the flow of water, tides, and currents affect the seafloor. We can define where species are likely going to be found based on habitat studies and based on what the seafloor looks like, right? So different fish are going to live in kind of a rocky area compared to a sandy area compared to a corally seafloor. This is really important for many commercial fish species and can help us better define areas for fishery assessment surveys and areas that are untrawlable. So, right, fishing trawls, they take their nets and they drag it across the seafloor to catch up fish. But we wouldn't want folks to be dragging their nets in a really rocky area because that's going to destroy the habitat that's down there. It's going to rip up the nets. It's not going to be good for anyone. So we want to identify those areas early so that people can stay away from them. Additionally, and we mentioned corals, but it helps identify also critical sponge habitats, which are really important for a variety of different fish species. Additionally, the seafloor changes pretty frequently, whether it's from natural disasters such as tsunamis and earthquakes and hurricanes. These can influence the seafloor shape. In addition to glaciers, right, we've got a lot of the glaciers eroding and influencing the geographical areas around them currently. So as those glaciers retreat and melt, they'll drop some larger boulders or some other chunks of ice or rocks, or they'll create little walls as the glacier is scraped across the seafloor. And glacier visitation is a huge tourist attraction, so we want to make sure that any cruise ships or tourist boats or whatnot can get as close as possible and safely possible to that glacier. Additionally, our data goes to support a lot of port and coastal communities, right? Over 90% of the goods the US receives have traveled on a boat at some point in time. And most of those are along each region of the coast. There's ports in every coast that receive a variety of different products, whether it's from agricultural to industrial to physical, just merchandise. And the Nautical Charts really focus heavily in those port areas, as well as supporting other US agencies such as the Coast Guard and the Army Corps of Engineers. So this is important because the depth of how much boat is underneath the water has changed significantly over the last couple hundred years. So in 1807, the average draft of a vessel was 10 feet, and that's how much water, how much boat is below the water, right? So similar to that iceberg comparison that everyone always is hearing, you've got part of the boat sticking up above the top of the water, but how much of it is below the water that we care about? And how much of it is going to, how far off the seafloor is the bottom of the boat? So as I mentioned, in 1807, the average draft was 10 feet. And as we move towards today, the average draft of a vessel is now 50 feet. So that is a significant change. And in most places, the seafloor hasn't changed drastically that much, either hasn't gained 40 feet deeper, hasn't got 40 feet deeper, unless, of course, by dredging. But we need to know how much room there is between the bottom of the boat and the seafloor in order to make sure we can get vessels to and from safely. And as we can see here again, this is the big ship coming into a port. We've got a lot of other factors that we need to consider as well. as in changes of tide. That's going to change where the boat physically sits in the water. That's also then going to affect of how much clearance the top of the boat has to a bridge or a crane or other features in the waterway. And again, we care about that under keel clearance. The keel is this bottom line of the boat here. What is the distance between the keel or the bottom of the boat and the sea floor? And you can see kind of in our little snorkeling view here of the water, we've got some coral heads on this side and we've got some coral heads on this side of the boat. So we need to know where those are so the boat can find a clear path to move forward. And additionally, here at Office of Coast Survey, we're responsible for upgrading and updating the nautical charts or ocean maps and surveying the ocean bottom and responding to maritime emergencies, whether that's vessel sinkings, tsunamis, hurricane oil spills. We're there and searching for any underwater obstructions that might pose a danger to navigation from any of those events. So in our top left corner here, we can see this kind of container ship that's not doing too well, and the containers are kind of probably going to fall into the water if some of them already have not. So we would go in and we would try to find these shipping containers that may have spilled into the water and that may be posing a threat to navigation currently. In addition to why did the vessel turn sideways? Did it strike a rock? Is there something else in the channel that we're not aware of? We would survey to investigate that as well. The pilots on board, so each pilot is someone that knows the area super specifically and studies the waterway like the back of their hand, and they're familiar with all the nooks and crannies of the waterway. So we can kind of see 3 stages of photos here. This picture of a laptop in the bottom left-hand corner is what the pilot is looking at on the bridge or where you drive the ship. So we've got all these containers in front of them. We've got the chart on one side. We've got our position of the vessel on the other side. So we have a really accurate location of where the ship may be. And then over to our right here, we've got kind of, again, this complicated turn that this long ship is going to do, and that there's not much room for error in, because as you can see, as the ship turns, it basically takes up the width of the navigable waters here. So we've got kind of this pointy landmass off to our left and this other pointy landmass off to our right. And we can see that there's not safe water all the way up to these pointy landmasses. The safe water is solely right in the middle of this waterway here. So it's really important for the captains and the pilots of the vessel to know where exactly the ship is so that they can maintain that safe waterway. And then off to our right here, this is kind of an aerial image of what this middle image is, right? We've got our pointy piece of land off to the left. We've got our terminal shaped looking land off to the right here. And we can see that the boat here is trying to stay right in the middle of these 2 points to avoid any hazards that may exist in the water. Awesome. So I'm going to ask this question to the audience. How much of the US seafloor, including the oceans, the coasts, the Great Lakes, rivers, and whatnot, do we think is currently mapped? And to help you out, I'm going to give you a couple multiple choice answers. One, about 25%, about 50%, we're almost there, 75%, ooh, we're almost done, or 100%. We have completely mapped all the waters in the United States.
Okay, so for all of you guys out there with your keyboards in front of you, you can look for your question box, and I see the answers are pouring in. We've got Susan says 25%, Isabella says 50%, Karen says 100%, Tegan and Pascual and Juan Pablo say A, which is what, the 25%?
25%,
and
yeah.
Let's see, we have a couple other 25%. Susan says in Alaska it's about 2%. A lot of A's and B's, 25 to 50%. I think that seems to be the consensus here, is somewhere between 25 and 50%.
Awesome. Well, thanks everyone for participating. And I'm going to say everyone that selected B, you are correct. But I do really like Susan's answer that Alaska is about 2%. Because if we move to our next slide here and we look at this map of the United States and all of the waters that we are in designation of, we can see the red on this map represents areas that have not been charted with accurate or modern data. So we can see Alaska's got a lot of red around it, with the exception of some offshore areas in the southeast and some work up here north of Nome. So we can see, Susan, I appreciate your answer and I indulge in it fully. Additionally, we can see kind of right, we've got a lot of offshore surveys done here in the West Coast, but there's this weird gap here on the coast and then offshore. We've got a lot of work to do out in the Pacific Islands and then off the Gulf of Florida and the Great Lakes. And you might be thinking like, hey, I'm pretty sure that vessels travel and operate in these areas all the time. There must be some kind of data there. Yes, and Jess is going to talk a little bit later about the different techniques of how surveying's evolved over the years. And there is, in fact, data there. It was just not collected with the most accurate, up-to-date information. And as we mentioned, right, the seafloor can change quite a bit. There are some places in Alaska that I've specifically have surveyed where the area hasn't been surveyed in over 125 years. A lot of things have happened in 125 years, and we can produce a lot better results now than were able to previously, and we can do it a lot quicker too. So with that, I'm gonna ask, are there any questions?
Okay, so if you want to hide your slides for a bit so we can see you full screen, that would be great. And Isabella had a question from way back. She was wondering, what do the pins on your uniform mean?
Oh, great question, Isabella, on this side. So I am a NOAA Corps officer.
So Michelle, if you want to hide your slides, then we can see the pins a little closer up.
There we go.
There. Okay.
So I am a NOAA Corps officer, which is one of the 8 uniform services of the United States, and there are the 6 military, and then 2 public service uniform services. There's the Public Health Service, and then the NOAA Corps. The NOAA Corps is the smallest of the services. We've got about 321 members, and similar to the military and other branches of service, you get little ribbons for doing certain things. So that's what I've accumulated so far in my career.
So Pasquale had wanted to know, what's the favorite part of your job?
That's a great question, and I love answering it because it's getting to do events like this and public outreach. It's amazing how much maritime navigation and different environmental science aspects impact our daily lives and we don't even know it. And so I really like communicating and supporting that message.
Great. And we had a question of Juan had wanted to know, how did you get your job?
How did I get my job? That's a great question, Juan. So I graduated college with a generic degree in environmental science, but specifically in aquaculture and aquarium tank design. So I spent a lot of time building fish tanks and different tanks for raising clams and oysters and whatnot, and I really enjoyed doing that all throughout New England, all through college. Then after graduating, I was living down in Virginia for about a year, doing the same thing, raising clams and oysters, and specifically designing systems to feed baby clams and oysters, which was pretty fun. And I really liked what I was doing, but I didn't like where I was living. And in college, I had a classmate who was a couple years older than me, Lieutenant Dan Palance. He's still a NOAA Corps officer. We were kind of friends, but he had come back to do a presentation on the NOAA Corps. And of course, I didn't go to it because I already had a job after graduation, and why would I care? But my advisor was smarter than I was, and he pulled me into his office and he sat me down and he was like, I know you already have a job, but I think you should keep the NOAA Corps on the back burner. It seems like something you'd be really good at and something you'd really enjoy. So after living in Virginia for about a year and not really liking so much where I was living, I really wanted to go to Alaska, and I remembered the NOAA Corps, and I submitted my application, and 6 months later I was in a boat sailing up to Kodiak. So that was pretty exciting. And I have really enjoyed it so far since. I like the variety of my job. I get to kind of move around to different places every 2 to 3 years and try out different roles and responsibilities. I don't spend a lot of time at a desk, which I really enjoy. So.
And in a related way, Michelle from Hawaii had wanted to know, do you captain a boat? So currently, as a NOAA Corps officer, your job kind of switches every 2 to 3 years. So you spend about 2 years at sea on a boat, maybe not necessarily as a captain, but you are responsible for certain times of the day for driving the boat and acting and navigating it safely and completing the boat's mission. In my current assignment, I am captain of a 34-foot little survey boat, and we have a team of 3 that we complete surveys here in the Pacific Northwest for. Great. Well, I know that we want to get on to how we do the mapping, so maybe at this point I will pass it off back to you and Jess.
Awesome. Well, thank you, Lisa. All righty.
Okay. Thanks, Michelle. So yeah, so now I'm going to talk about how do we actually map the seafloor. So Michelle was talking about sound. So we were talking about using sound today, using sound to map the seafloor. So currently we use sound, but historically we use different tools. Historically, we used something called a lead line. And a lead line, I have one here, is exactly what it sounds like. And it's just as heavy. It's a piece of lead. You can see this here. It's really heavy. Ooh. And it's attached to a really long line, a long piece of rope. And the rope is measured. So this one's measured in meters. So the surveyors would take that lead line, they would take the lead end, put that over the side of the boat, it would sink to the seafloor, and then they would count the little flags on here to get their depth measurements. So this is obviously really heavy. I have trouble picking it up just once or twice. So this is a really inconvenient way to take depth measurements. And you're taking one depth measurement, moving on to a different area, taking another depth measurement, moving on to another area. So you don't get very many depth measurements with this. You don't get a complete full picture of the sea floor. So we wanted to use something better, something different, something that we could survey the sea floor with and give us better coverage. So now we use sound, and we use sound in a manner similar to echolocation. And you guys have maybe heard of echolocation. So my question for you is, what is echolocation? So you can type in your answers and send them in to Lisa, or you can just think about it on your own at home. What is echolocation, or what types of animals use echolocation? So Lisa, are we getting any good responses?
So we have a couple of responses here. Let's see whether, yes, we get dolphins, and Shelley said bats use echolocation. Eve also said bats. Paul said it's how animals chat under the water. Tegan says it's the way some animals hear or see their prey. Paul said that whales use echolocation. So it sounds like we've got a variety of animals here.
Yep, you guys are all right. Those are all really great answers. So echolocation is basically how some animals, so some marine mammals use echolocation, and bats use echolocation. And it's basically just emitting a sound. So they're putting a sound out there. It's bouncing off of their prey or another object in the ocean. It's bouncing off of that and coming back to them. So they're basically listening for that echo to locate their prey or to locate objects around them or to learn about their environment. So we use echolocation, and we use it called sonar. And maybe you guys have heard of sonar before as well. But sonar stands for sound, navigation, and ranging. So we're using it some people use it to navigate, but ranging also means determining the distance of something from you. So determining where an object is. So we're actually using sonar to determine how deep the seafloor is. So the sonar unit, or the sonar, will be mounted on the bottom of the ship. So you can see our sonar unit down at the bottom of the ship. And you can see an example over here on the right where the sonar is mounted on the bottom of the ship. Yeah. So when we're actively using this, when we're using the sonar, it emits a ping. We call that sound a ping. So we're pinging the seafloor with sound. That sound is emitted from the sonar. It hits the seafloor, bounces back up to the sonar. So the sonar is basically listening for that echo. So we're using echolocation to determine the depth of the seafloor. And we determine the depth of the seafloor by using this equation down here. So the depth equals the speed of sound, which we also have to calculate, times the time that it takes for that ping to leave the sonar unit, hit the seafloor, and come back up to the sonar unit. So that's how we determine depth of the seafloor. So in this next slide, I'm going to talk about why we use sound. I mean, why do we use sound to survey the seafloor in the first place? So sound is a wave, just like light is a wave or radio is a wave. But unlike those other types of waves, sound actually travels better through denser mediums. Most other waves travel slower through denser mediums. So if you think about light, traveling through water, it gets absorbed, it gets scattered, it gets reflected really easily. So light doesn't penetrate water very deeply. So sound, on the other hand, actually travels better, faster and further through solids. So it travels through denser objects like this solid better than it does through like a liquid, but it travels faster and farther through liquids, so like seawater, better than it would through air. So sound is a little bit different than like light waves. It travels really well underwater. So it actually travels 5 times faster in water than it does in air. And it travels about 1,500 meters per second in water. And that meters per second, that changes a little bit with the density of water and some other characteristics of water. So my next question for you guys, what factors affect the speed of sound through water? So this is multiple choice. So is it A, temperature? So how hot or cold the water is, does that affect the speed of sound? Salinity, how salty the water is, does that affect the speed of sound? Depth of the water, or D, all of the above? So what do you guys think affects the speed of sound? So I'm gonna wait for Lisa to kind of give us some feedback, read the answers that are coming in. So Lisa, are we getting any answers from?
Oh, sorry, I was on mute. So we are getting answers. Susan and Isabella, Allison, Shelley, Paul, and Elizabeth are all saying D. Juan Pablo says C. Tegan said B and C or D. Mary Hopkins said D. A lot of the rest of the people, Mary, Michelle, Pasquale, Tom, are all saying D. So
yeah.
Can you help us out here?
Yeah, so you guys are actually all right. So it is D, it is all of the above. So temperature, salinity, and depth all affect the speed of sound through water. Temperature makes the higher the temperature, the faster the molecules are acting in water. So if you think about boiling water, those molecules are bouncing around and bumping into each other really quickly. They're moving really fast. So that actually, that warm water, that warm temperature actually increases the speed of sound through water. And then salinity actually increases the density of water. So the density of water, the more dense it is, the faster the speed of sound. And then depth, the deeper you are, the more pressurized the water is. So at deeper depths, more pressure, the molecules are more tightly packed together. So that increases density of water as well. So the deeper the water, the more dense it is, and the faster the speed of sound. So when we're surveying, we actually have to take into account the differences in temperature, salinity, and depth. So when we're out there surveying, we use this device on the right side called a sound speed profiler. And this will measure temperature, salinity, and depth for us so that we can calculate the speed of sound through water, because it'll change if we're moving through the water. So if we're closer to fresh water, it'll be different than if we're out in deeper salty water. So we're constantly having to measure the speed of sound through water. So do you guys have any questions before we move on? I think, so Michelle's going to talk more about surveying and the data that we acquire and what that tells us about the seafloor. But do you guys have any questions about sound before we move on?
Yes, actually there were some questions from some of the previous slides, and if anybody else has questions, please type them in. So Susan was asking whether the ship that you had where you were showing the ping going down to the bottom, whether that was the Rainier, the NOAA ship Rainier.
I don't know. I think it's Michelle, can you go back to that slide? I think it was the Rainier. I think it was S221. Yeah, I think that's the Rainier. So that the S221 is one of our vessels. So we have the Rainier and the Fairweather on that west coast.
But you can see that the little boats along the side of on top of the boat that are used for the near shore charting. So that's one of the ways that I'm able to tell the NOAA charting boats from the other boats.
Yeah.
Yeah. So
and Michelle will show that. Michelle will talk a little bit more about our survey vessels in her next presentation, or in her
Sounds good. Mary wanted to know, how do you like mapping? How do you like making charts?
It's interesting. I've learned a lot. I think a lot of people don't know about the profession or really think about the profession until you're introduced to it, really. So a lot of my coworkers have come from backgrounds in oceanography or marine geography. Some of them worked on the vessels before they worked in the office. So a lot of it's interesting. I've learned a lot. So it's also challenging. So because there's a lot of physics and things that go into it.
Sounds good. Well, I know we have a lot to cover, so maybe we'll move on from there and we'll go to the next section.
Okay.
Great, thanks, Jess. So today now we're going to move on to our actual survey area. So we are going to go out and we are going to survey. So we're focusing today on the southwest Prince of Wales Island off just to the west of an island called Dawes Island. And how are we going to do it? Well, we have our two lovely West Coast survey ships, the NOAA ship Fairweather and the NOAA ship Rainier. As Lisa mentioned, you can always tell the survey ships by the number of small boats on the side of the boat. So both Rainier and Fairweather carry 4 survey launches, which are these little tiny smaller boats here. Each one of these launches has a sonar on the bottom of the boat, in addition to the ship. So each ship has 5 sonars on board to get the survey done. So cumulatively for this Dawes Island survey, we've got Rainier, we've got Fairweather, we've got 10 sonars. We are going to cruise through this project like no tomorrow. The survey boats you deploy them over the side, and then the little boats head off on their way to get their jobs done. Fun fact, the NOAA ship Rainier and the NOAA ship Fairweather are both over 50 years old. So now we're going to watch a little video on how the multi-beam sonar works. And I'm going to hit play here. So here we see a ship traveling across the seafloor, and the kind of triangular beam that's coming out of the bottom of the ship is representative of the sound waves that are traveling through the water, hitting the seafloor and bouncing back up to the ship. And this rainbow color shows the kind of data that we collect along the way. So as we go ahead and we collect this data, what the seafloor looks like becomes these beautiful kind of 3D images. And we can see here in our top left photo, we've got this kind of dynamic looking ridgeway under the sea or on the seafloor. The purple here being the deepest part of the water, and then the red and yellow and orangey colors kind of being the shoalest, or the part closest to the water surface. In our bottom right photo here, we've kind of got a similar image of a canyon. In the center of the canyon, we see our deep purples and blues, and then up towards the edges of the canyon, we see our reds and oranges. And these provide really vivid images of what the seafloor looks like, right? So if we were to take our binoculars and put them underneath the water surface and remove any imperfections or items and factors that keep us from seeing through to the seafloor, this is kind of what it would look like, just not as rainbow colored. Additionally, we can get really good images and representation of items on the ground, such as shipwrecks. So we can see here that this is kind of a little bit more fishing boat or trawler shaped. The one in the bottom left is a little bit more recreational vessel shaped. And this one in the middle here in the bottom has probably been down there for a little while because it's broken up into 2 pieces. So in our survey area that we're talking about here, our depths range from 0 to 254 fathoms. And in Alaska, because a lot of the area is really, really deep, we do our depth measurements and our charting representation in fathoms. And 1 fathom is about 6 feet. So whenever someone tells you, oh, we need to be 6 feet apart for social distancing in response to COVID-19, you can say, oh no, I'm going to be 1 fathom apart. It's exactly the same thing, but you sound pretty nautical. So in this chart image here we have to the left, we can see kind of these red and orangey colors that we talked about before. Again, that's some really shoal area. And we can see what's pretty cool is that the shoalest area, so the shortest distance between the surface of the water and the ocean bottom, is closest to land, which makes sense, right? Like the land is just part of the ocean bottom that isn't underwater, so it's just bottom, right? As we move further away from the land, we kind of get this nice deep canyon and ravine in the center of this channel here. And this is where we want to make sure on our chart we represent and boats can know it's safe to navigate. We're going to take a more 3D image of this canyon again, and we can see right here in the middle, we've got those deep blues and purples, and this is where we want to make sure ships try or navigate, because to the left and to the right of the canyon, it looks a little rocky and uncomfortable, and we wouldn't want any vessel to hit that. In our canyon walls here, we can see a little bit of these kind of black holes in our data, and what these are is it's representing something that is above the water line, right? So the data that we see is representation of everything that the sonar can collect information on below the water, below the surface of the water. There are some features though that are both in the water and out of the water at the same time, some of them being rocks. Similar, I'm going to go back to our iceberg reference here. Just like with an iceberg, you've got the tip of the iceberg, but usually there's a much larger mass underneath the iceberg. Similar with the rock, you might see the tip of a rock sticking out of the water, but there's going to be a much larger portion of the rock under the water. As you can see here in our kind of surface that we have to the left of what this shoal or shallow area looks like, there is a small hole right in this red coverage. So if we look at it a little bit closer, all of these dots represent individual points of sound that our sonar has collected, which is pretty cool how much sound we have built up over this rock. And we can see in our little point cloud that there is in fact a gap. So what we would know then is as the field unit, we're going to need to go back to this area and we're going to need to see what that rock looks like above the surface because we don't have an accurate picture of it in our data set. So as we continue collecting more data and processing along, we're going to group different depths based on kind of contour lines. So if you guys are hikers or whatnot, you probably are familiar with contour lines, but contour lines are just lines that group together certain depths. So we had talked about, for this survey, it ranges from 0 to 254 fathoms. So this deep purple down here and this contour line surrounding it is probably going to be anything deeper than 240 fathoms is going to be representative of this line. And then each one of these lines represents a different depth grouping as well. So if we were going to hike this area, we would not want spaces where the lines are really close together because that means it's a really steep depth or incline change. We would want places that are a little bit more spaced out because it wouldn't be as hard to climb uphill. Do we have any questions on how we collect the data and what the data looks like as we're collecting it?
Yeah, actually we had a question. Pascal had a question from earlier about lead lines, and she was wondering, can lead lines hurt sea life?
That's a great question. So again, lead lines are big heavy things on the bottom of a rope. So if in the chance that there is a large object or a sea life creature underneath the lead line at the exact moment that it is being dropped, it could potentially hurt, right? You wouldn't want to get hit by surprise in the head with a large piece of lead, but the lead line, as it does travel down through the water, is pushing the water out of the way. It doesn't travel very fast, so I am hopeful that marine life would be able to move out of the way before the lead line hits. In our modern surveying for our sonars on the bottom of our vessels, we do not operate at such a low frequency that marine mammals can hear it. We are above the threshold. We operate at above 200 kilohertz for marine mammals to hear it. So our sonars do not impact marine mammals. We also do practice that if we do see marine mammals in the area within 1 nautical mile of where we're surveying, we just stop and let them go by. We're in their home, we're visiting, so.
Well, I have a question from Katya about fish, actually. She was wondering if fish get in the way of the sonar when you're trying to map the ocean bottom.
They absolutely do, and we get these really cool data sets of like just fish balls hovering above the seafloor and certain types of fish and in certain areas, particularly on the East Coast with our East Coast surveying using Sidescan, which Jess going to talk about in a little bit. You can get these really fun images of different fish and dolphins and whatnot near the sonar and playing. So dolphins really like Sidescan Sonar.
That's pretty cool. And then Paul had wanted to, Emma had wanted to know, would boats be able to fit in the green and yellow area on that map that you had of the canyon?
Yeah, that's a great question. So most boats would. So each boat kind of operates at a different depth, or how much under clear, how deep their boat is, like what is the difference of the measurement of the boat below the water surface. So I would say so. This probably is at least 60 meter or 60 fathoms. So most boats, most recreational boats have a depth of 7 to 10 feet, or just over a fathom. So they probably could operate in this area. I do not know off the top of my head though what the yellow and green depths here represent though.
Okay, well, great. We have a question about the Coast Guard, but I think that I'm going to hold on to that one for now, and because I know that we have a little bit more to cover, and maybe if we have time, we can cover that one at the end.
Awesome, great. So now that we know the depth of the seafloor, we're going to talk about what other information that we have from this data set that we've just collected. So one of the big things is, right, we now know where the seafloor is, but what are the characteristics of the seafloor? Is it hard or is it soft? And that information we can learn about from backscatter. So backscatter is the intensity or the strength of the returning sound wave. So the best way to explain this is if you have a tennis ball, and if I drop this on the surface of my desk here, it's going to bounce up pretty quickly and pretty easily. If I have I have a hard desk, so that bounced up pretty quick. If I take it and bounce it on the soft, squishy little hard drive case, it's not going to bounce as easily, and it's going to roll all over and make a mess. So the strength of the returning sound wave is similar to the tennis ball. The tennis ball bounced back, had a much stronger return based on the hard surface, and a much softer return based on the squishy hard drive case. So similarly, we can find out the same thing about the seafloor. So a harder bottom is going to return a stronger signal, just like the surface of my desk here. And a softer bottom is going to return a weaker signal. And these are represented by the harder surfaces are more corals and rocks, and the weaker signals are more soft bottoms such as sand and mud. We can then use this information to create detailed 3D maps of seafloors and habitats present on the ocean bottom, with the goal of improving safety of navigation and marine ecosystems protection. So let's take a look at what some of the backscatter in our survey area looks like here in Dawes Island. So as we can see, we've kind of got this little, remember our channel here in the middle, that deep area. We're going to focus in on this one particular corner in the southwest that is more towards the island itself and in a little bit shoaler of an area. So we can see in the background here our multi-beam information. And again, the red are the shoaler parts of closer to the ocean, the water surface. And our orange here is kind of that deeper, so further down than the red areas are. And then overlaid on this, we have our backscatter. So again, the backscatter is the strength of the returning sound signal. And we can see in these kind of clustery shoaler areas, the areas that are closer to the ocean surface, that it has a very, very light white return, or a light gray return. And that represents a hard surface, such as the rocks. If we go over here, we can see in these flatter, smoother areas that it's a little bit more dark gray. So, and that represents a softer surface, such as sand or mud. So to confirm these speculations that we have, we do go out and we do collect bottom samples. And these are targeted locations based on kind of our backscatter representation and analysis. These are targeted locations where we want to ground truth what we're seeing in the data collected. So we'll go out and we have these kind of, this bucket type system, and then this little guy down here that we call the nibbler, because it just gets a little niblet of the seafloor. And what these do is we deploy these over the side of the boat or the launch or the ship, and we are trying to grab a piece of that ocean bottom so that we can determine what the actual ground characteristics are. So you'll see here in the top right corner, kind of this pile of gray gush. Well, that's mud. And then over here in the center, we've kind of got some cobbles and rocks that would be on the chart as rocky or cobbly. And then down here in the corner, we've got a combination of some sand, we've got some shells, we've got some broken shells, we've got some rocks. So that would probably be characterized as broken shells. And this is all information that ends up on the chart, but Jess is going to talk about in a moment here. The sand, this is all then characterized into different sides. So, okay, we have mud. Is it sticky? Is it dry? What kind of mud is it? What is the grain size of the mud? And all this information does help the mariner and for fish habitat mapping of where is a good place to anchor, where would be a bad place to anchor. A good place to anchor would be somewhere sticky that I know my anchor is going to stick into, like mud or sand. Bad place to anchor would be something with just a bunch of rocks, because I know my anchor is never going to dig into the ground there. Similarly, if I'm fishing for a certain species of fish, I can know that they live in a rocky environment. So that information is going to help me along the way. Do we have any questions on that?
Okay, we have a couple of questions about whether Mary had asked what can the sonar go through animals, and I think you kind of addressed that a little bit with the fish, but I think she was wondering about that.
Yeah, absolutely. So that's a great question, Mary. So the sonar doesn't per se go through animals in a way an X-ray would for you and I. It kind of just creates a image or sounding around the animal. So it would create a reflection off the animal's skin, but it wouldn't hurt them. And again, if we do see marine mammals in the area, we do stop surveying until the mammals have passed by.
And then Janet had wanted to know how kelp forests show up in sonar when you're surveying.
That's a great question, Janet. So the kelp forests are a little hard to map because we don't want to destroy the ecosystem in the area that we're in with our boat props and boat motors and whatnot. But if we can't get in there to map the area, it's probably not a safe place. We want to make sure mariners and other boaters know it's not really a safe place to be navigating to begin with. So we will mark those areas on the chart as kelpy, and they have this beautiful little kind of floral symbol that shows up on the chart.
Okay, I know that we want to get through a couple more sections here, so I'll let you go on and pass it over to Jess at this point.
Great. So I will pass it on to Jess now.
Okay, so hi everybody, thanks Michelle. So Michelle talked about our primary tool that we use for mapping. So that sonar that's on the bottom of our vessel, we call it a multi-beam sonar. That's that sonar that's mounted on the bottom of our vessel. So we do occasionally use other tools for mapping as well, other tools to give us a better idea of the seafloor. So just one of those tools that we use is a Sidescan sonar. And we typically will use this at the same time that we're using that main multi-beam sonar that's mounted on the bottom of our vessel. So we'll use these at the same time. The Sidescan sonar, however, it does not emit sound vertically through the water column. It doesn't emit sound down. It emits it out to the side, and then that sound will hit an object or something on the seafloor, like a rock or some other object. It hits that object, and it casts a shadow on the other side. So we call that an acoustic shadow. And we can actually use our software to measure the shadow to determine how high off of the seafloor that object is sticking. So Sidescan is really great at giving us shadows and imagery. So unlike our other sonar that just gives us like pings that give us points, Sidescan gives us images. And we can see a couple of shipwrecks here in these two images, and you can kind of get a lot of information from the shadow. This first image on the left looks kind of like a big Navy ship, maybe just from like looking at that outline of the shadow. Yep, and then this one on the right, this other vessel, kind of looks more like a tugboat maybe. You can see that wheelhouse. Maybe it's a fishing trawler. And then with the software that we have, we can actually measure the shadow to determine how high off the seafloor it's sticking. So, and then from this third image, just from that shadow, you can see it's a plane, right? So you can see the wings of the plane, you can see that tail of the plane. And we wouldn't be able to tell that that was a plane without that shadow, because that object, that bright white object right there, it's nose down in the seafloor. So you can't really see the whole plane itself just by that object, but the shadow tells us a lot. So sometimes we use Sidescan Sonar. They're really useful on the East Coast of the US because the East Coast tends to be more gradual and flat. So those shadows that we get from the side scan show up really well in shallower, gradual, flat areas. So like on the East Coast. We're also always looking into developing new technology, new programs, new tools. So new tools to help us survey the seafloor, but also new programs and tools that we can give to the mariners to better navigate. So we're looking at unmanned surface vehicles. So these surface vehicles will also have sonar on them. So we can use them at the same time that we're using our manned vehicles. So we'll have another tool out there that we can use to survey the seafloor in addition to our manned survey vehicles, which is great. We're also looking into using unmanned aerial vehicles, so like drones. You guys have probably heard of drones. So we can use these to help us give us information about coastlines and near shore areas. So we're looking into both of those different types of technologies, and then we're also always developing new programs and tools for our users. So those, and we're specifically looking into developing programs for those captains of those big vessels, those big tanker ships, the big cargo vessels that Michelle was showing you earlier. They have very little room to navigate sometimes, little room for error. They have to navigate very precisely through some of these waterways. So we want to give them really precise, updated information. So we're working together to give them really detailed information about the seafloor, but also putting in information about surface currents, surface waves, what the water levels are like. So all in an effort so that they can navigate very precisely through challenging waterways. So, and then for, do you guys have any questions about that really quick before I move on?
I think we have a couple questions, but we can wait until the next sections.
Okay, yeah, the next section is pretty quick, so. Okay, so nautical charts. So we've kind of mentioned charts and navigating. So Michelle and I work with the Office of Coast Survey, and in the Office of Coast Survey, our primary concern is making charts and for mariners to navigate safely. And charts will contain depths and depth contours and all this information about the seafloor that we've acquired. So we're going to look at this survey again that Michelle took you guys through earlier, this survey that's off of Doll Island in Southeast Alaska. So remember, there's that channel in the middle. It's like 250 fathoms, I believe, 254 fathoms. So a channel that goes down the middle. There's those red areas. Remember, those red areas are a little more shallow. And then all of those white areas, those gaps of data, remember, are those rocks or the islands, those areas that are above the sea level, above the water line that we can't take our sonar over. So we'll use those gaps. So we'll use those gaps and fill those gaps in with rocks on our chart. So we're going to take those contour lines. We're going to start with the contour lines that Michelle talked about. And remember, those contour lines show everything along that contour line is the same depth. So we're going to take those contour lines, we're going to use the depth of the seafloor, and then we're also going to use that bottom sample information that we got when we were taking bottom samples. So for this survey, we got 3 bottom samples in this area. So that one is RKY, means rocky, so we had rocks in our bottom sample. The S means sandy, so we had sand in our bottom sample, and then the M means muddy, so we got mud in our bottom sample at that location. So we're going to put all of this data on the chart. So this next slide kind of shows how that chart is coming together. So you can see that seafloor data that we've got, and it's transparent at this point so that you can kind of see the chart beneath it. So we filled in some of those gaps with islands and land and rocks. And on the next slide, you can see just the chart by itself. So those depths are there. So all of those numbers on the chart are depths. And then we have the contour lines as well. We've added the contour lines to the chart. And then information from our bottom samples. So that RKY is on there, the S is on there, and the M are on there. They're kind of small, but they're on there. And then the charts also tell us a lot of other information about the waterway. So it gives us information about the aids to navigation. So those lights and buoys that are out on the water, those will be added to the chart. Any obstructions or shipwrecks that we find, like you saw with the side scan or with our multi-beam, if we find shipwrecks out there or obstructions or debris, that stuff will be added to the chart as well. So Michelle and I and all of our coworkers are out there gathering all of this information about the seafloor, and all of that gets applied to the chart, but then it also gets saved and archived, because remember, we want everybody, we want scientists and researchers and managers and students and teachers and everybody to be able to access our data for their own research or for their own general knowledge. So all of this data that we collect is on a website and it can be downloaded or saved, or you can request data if you can't find it. So we go to all of this trouble to collect all this data. We want it available for everybody to use. So that is kind of the end of our presentation. Michelle and I talked about why it's important to survey the seafloor. There's so many different reasons for surveying the seafloor, how we do that, how we use sound, and the tools that we use, as well as the data that those tools give us and what we can learn about the seafloor from that data. And we talked a little bit about navigation and nautical charts. So if you guys have any more questions, Michelle and I will be happy to answer you guys.
Okay, so we did have a question from Katya about Sidescan Sonar. She had asked, does the Sidescan make a shadow on animals, or is it just like ships and things?
No, it does. So Michelle kind of mentioned that a little, referred to that a little bit earlier. So we do occasionally, we'll see the shadow of fish schools or whales or dolphins, marine mammals down there. So it will bounce off of the marine mammals. So if it bounces off of anything or goes over anything, it's casting a shadow. So that acoustic shadow. So yeah, marine mammals create shadows in our Sidescan Sonar.
And actually, Beth had a related question about the Sidescan. She was asking if did you guys use the Sidescan sonar to find sunken battleships from previous battles in the Pacific?
We do have I mean there are a lot of ships that have been charted, so I don't know, Michelle, do you have any more information? So we do have a lot of charted ships on our charts in the Pacific. So there are some we are not allowed to chart and some that can be charted. It depends on the history of vessels. It depends on, so if maybe there's a story behind that. So if people died on the vessel, we may not want to chart that for privacy reasons. So not all wrecks that we find are charted.
Okay,
Yes,
and then go ahead, Michelle.
Oh, no, I was just agreeing.
Okay. Well, we're almost out of time, but I had wanted to say that Shelley had asked if there is a link to the data. And so I know that all of the Office of Coast Survey data is available on the web. So what we'll do is we'll put a link to that website onto our NOAA Live Alaska website in relation to the webinar that we just presented. And we also have some educational links that are Michelle and Jessica provided to us that have activities for kids to learn about charting. So so there is that. And I wanted to say thank you to Jessica and Michelle, and thank you to you guys all for coming and watching our webinar. Do you guys want to say anything to close out?
Thank you guys all for attending. It was really great. I wish we could be in person doing this again, but it's really great to have the opportunity to do this webinar anyways. So thank you all for attending.
Yes, and stay safe, keep each other safe, take care of someone else if you can, and safe navigating too.
Great. And so thank you all of you guys. Next week we are taking a week off because Tuesday is election day and there is a lot of stuff going on. So the following week, on November the 10th, we'll be back with Summer Ollendorf from the Tsunami Warning Center to talk to us about tsunamis. So please stay tuned. Thank you for attending, and we will see you next time. Bye-bye.
Thank you.
Bye.